For centuries, humanity has gazed upon the cosmos, attempting to unravel its deepest secrets. From the slow, majestic dance of the planets to the fiery birth and death of stars, we've meticulously charted and understood so much of the visible universe. Yet, there remains an overwhelming sense of the unknown, an invisible architecture that dictates the very fabric of reality. We measure, we calculate, we observe, and still, the vast majority of existence remains shrouded in mystery, an ethereal substance we've come to call dark matter. It's a testament to our intellectual courage, our insatiable curiosity, that we confront this profound enigma, this cosmic ghost, with an ever-increasing arsenal of scientific instruments and theoretical frameworks. We ask, what is it? And more importantly, can we ever truly see it? The story of dark matter isn't a recent one. Its origins are deeply etched into the annals of astrophysics, a journey spanning almost a century of observation and deduction. The first whispers of an unseen mass came in the 1930s, from the Swiss astrophysicist Fritz Zwicky. While studying the Coma cluster of galaxies, Zwicky noticed something profoundly odd: the galaxies within the cluster were moving far too fast for the visible matter to gravitationally bind them. He posited the existence of dunkle materie, or dark matter, an invisible component providing the necessary gravitational glue. For decades, his audacious claim remained largely unheeded, a peculiar anomaly in the grand scheme of cosmic understanding. It wasn't until the 1970s that Zwicky's hypothesis found its powerful corroboration, thanks to the pioneering work of American astronomer Vera Rubin. Rubin and her colleague Kent Ford were meticulously studying the rotation curves of spiral galaxies. The prevailing understanding was that stars closer to the galactic center would orbit faster, while those further out would slow down, much like planets in our solar system. After all, the vast majority of a galaxy's visible mass is concentrated at its core. But Rubin's observations consistently showed something entirely different. Stars on the outer edges of galaxies were orbiting at roughly the same speed as those closer to the center. This flat rotation curve was an astonishing discovery, defying all conventional gravitational physics if only visible matter was considered. It was as if an invisible, massive halo was enveloping these galaxies, exerting a gravitational pull that kept the outer stars moving at an unexpectedly high velocity. This invisible glue was the dark matter Zwicky had spoken of, finally brought into the mainstream of scientific thought. Since then, the hunt for dark matter has intensified, becoming one of the most compelling quests in modern physics. We've come to understand that dark matter isn't just a minor constituent, it's thought to make up roughly 27% of the universe's mass-energy budget, compared to the mere 5% that comprises all the ordinary, baryonic matter we can see and interact with. The remaining 68% is dark energy, an even more mysterious force accelerating the expansion of the universe. This means that everything we perceive, every star, every planet, every atom in our bodies, is but a tiny fraction of what's truly out there. Dark matter, despite its omnipresence, remains stubbornly elusive, interacting with ordinary matter only through gravity. It doesn't absorb, reflect, or emit light, making it truly dark and incredibly difficult to detect directly. For decades, our understanding of dark matter has been largely inferential. We see its effects, the gravitational lensing of light, the large-scale structure of the cosmos, the aforementioned galactic rotation curves, but we've never directly observed the particles themselves. Many theoretical candidates have emerged, with weakly interacting massive particles, or WIMPs, being among the most favored. These hypothetical particles would be massive, as their name suggests, but would interact with ordinary matter only through the weak nuclear force and gravity, explaining their dark nature. And this brings us to a potentially groundbreaking moment in this epic saga. Recent research has presented what could be the most compelling direct evidence yet for the detection of dark matter. This isn't a simulation, a theoretical model, or an indirect observation of its gravitational influence. This is about observing the telltale signature of dark matter's direct interaction, not with ordinary matter, but with itself. The core idea is elegant in its simplicity: if WIMPs exist, and if they populate the halo around galaxies like our own Milky Way, then occasionally, two WIMPs might collide. And when a WIMP meets another WIMP, they could annihilate each other, much like matter and antimatter do, releasing a burst of energy in the form of gamma rays. These gamma rays would be distinct, possessing a specific energy signature, a cosmic fingerprint that could differentiate them from other high-energy phenomena in the universe. Researchers utilized data from NASA's Fermi Gamma Ray Space Telescope, an instrument specifically designed to detect these incredibly high-energy photons. The target of their scrutiny was the galactic center, a region long suspected to be a hotspot for dark matter interactions due to its immense density and gravitational pull. The challenge, of course, is that the galactic center is a chaotic, vibrant place, teeming with pulsars, supernovae remnants, cosmic ray interactions, and other astrophysical sources that produce a deluge of gamma rays. Sifting through this cosmic noise to find the faint whisper of dark matter annihilation is like trying to hear a pin drop in a thunderous stadium. The methodology employed was meticulous and rigorous. First, they obtained raw maps of gamma-ray emissions from the galactic halo. Then came the painstaking process of removing all known sources of background contamination. This involved identifying and subtracting emissions from pulsars, interstellar gas interactions, isotropic radiation, and even the Fermi bubbles, two colossal, enigmatic structures extending above and below the galactic plane that are also significant sources of gamma rays. Imagine stripping away layer after layer of obscuring data, like an archaeological dig, until only the purest, most fundamental signal remains. And what they found, after this exhaustive purification process, was astonishing. A clear, statistically significant excess of gamma rays persisted, forming a distinct peak at an energy level of approximately 20 gigaelectronvolts, GeV. The statistical significance of this excess, often expressed in terms of sigma, was remarkably high, between 13 and 19 sigma. To put that in perspective, a result is generally considered a discovery in particle physics at 5 sigma, meaning there's less than a 1 in 3.5 million chance it's a random fluctuation. This signal, at nearly 20 sigma, is almost unequivocally real. What makes this finding so compelling is its consistency with theoretical predictions. When researchers modeled what the gamma-ray signal from WIMP annihilation should look like, the cleaned observational data from the Fermi telescope closely matched these models. Furthermore, the characteristics of the observed signal, its energy, its spatial distribution, align beautifully with what we would expect if WIMPs were annihilating in the dense core of our galaxy. The models even suggest that the WIMPs involved in these annihilations are likely producing either bottom quarks or W bosons, giving us further clues about their fundamental properties. This isn't the first time an excess of gamma rays has been observed from the galactic center, known as the Galactic Center Gamma Ray Excess or GCE. Previous studies have hinted at it, but often with lower statistical significance or with lingering doubts about potential astrophysical contaminants. What sets this new research apart is the unprecedented level of data cleaning and analytical rigor applied, reducing the likelihood of misattributing the signal to conventional sources. Of course, in science, one discovery, no matter how profound, is rarely the final word. The scientific community will now engage in robust debate and replication efforts. Other teams will attempt to confirm these findings using different methodologies, different telescopes, and perhaps even by searching for similar gamma-ray excesses in other dwarf galaxies, which are thought to be rich in dark matter but relatively devoid of the complex astrophysical noise found in larger galaxies. There's also the tantalizing prospect of detecting these annihilation products through other channels, such as neutrinos, although neutrino detection presents its own formidable challenges. If confirmed, this would not merely be another incremental step forward, it would be a monumental leap. It would mean that we have, for the first time, directly seen the evidence of dark matter interacting with itself. It would validate the WIMP hypothesis, providing concrete evidence for a particle that has, until now, existed only in theoretical constructs. Such a discovery would fundamentally reshape our understanding of the universe, offering a tangible connection to the invisible scaffold that holds galaxies together. It would open up entirely new avenues for research, allowing us to probe the properties of dark matter particles with a precision previously unimaginable. The implications could reverberate across cosmology, particle physics, and our entire conception of reality. The cosmos is a tapestry woven with threads both seen and unseen. For so long, we've been trying to grasp the nature of those invisible threads, to understand the loom upon which our universe is spun. This potential detection of dark matter, this faint glow of annihilation, offers a glimpse behind the curtain, a moment of profound revelation in humanity's unending quest to understand its place in the grand, mysterious expanse of existence. The journey to fully comprehend dark matter is far from over, but we may just have taken our most significant step yet toward seeing the unseen. That's it for today. If you enjoyed this deep dive, hit that subscribe button. Stay curious, and keep your eyes on the skies. I'll see you in the next one.